Hello, welcome to our semiconductor education program. I'm Vincent Chang. In this video, I'm going to teach you part 2 of Class A upstage simulation. So I think through this lecture, you will get a deeper understanding and become more confident about knowing the circuit Class A upstage. So in the previous video, I have taught you about the positive saturation voltage, V capital M, is limited by the saturation of the emitter follower transistor Q1. And the saturation voltage is shown on the slide. VCC minus VC saturation. So in the case of the supply voltage of 15 volt, 0.2 volt, the positive saturation voltage will be 14.8 volt. In the other direction, in another direction, the negative direction, it will be limited by two scenarios. There are two scenarios. The first scenario, it will be limited by the saturation of Q2, which is the current mirror transistor. So here's the first negative saturation voltage. And the second scenario, it could be limited by the cutoff of the emitter follower transistor Q1. Okay, Q2 on the left, Q1 on the right. So in this case, in this scenario, the negative saturation voltage will be this. So you might be wondering, do you really understand this? Do you really confident about this when you face this kind of real situation? To answer this, that's why I designed this lecture. So two examples. Let me give you two examples. The first one, load resistance of 1 kilo ohm on the left. So example 2 on the right. The load resistance is 2 kilo ohm. So 1 kilo ohm on the left, 2 kilo ohm on the right. The rest of the circuit are the same. Okay? So the two circuits are the same except different load resistance. So here's the example 1. So through the simulation, you will get this. So you see, the negative saturation voltage is negative 10 volt. So why? I explained this in the previous video, right? So it will be limited by, because it is limited by the cutoff of the emitter follower transistor Q1. So negative 10 volt. So negative 10 volt. See the linear region, the positive saturation region, and the negative saturation region is limited by the cutoff of Q1. So the second example, so 10 milliamp, the bias current is still 10 milliamp, but the load resistance is now changed to 2 kilo ohm. So would this still be the answer? No. Why? So it's impossible to go down to the negative 20 volt. No. Because when you go down to negative 14.8 volt, something happened. So you know what happened. You know what happened, right? Because the transistor, the current mirror transistor, becomes saturated. Right, here's the answer. So linear region and two saturation region. So on the other direction, so this one, so you see the answer. You see the answer. So Q2 saturation, Q2. The current mirror transistor, so the answer is negative 14.8 volt. So negative 14.8, so 0.2 is very good approximation. It's a very good approximation. So negative saturation voltage, the conclusion. So two scenario, left. So you got kind of familiar with this, right? So on the left, Q2 saturation. On the right, Q1 cut off. So let's go a little bit deeper about the signal waveform. So let's say if we input a sinusoidal signal, the large signal sinusoidal signal, and then we examine the waveform of the different signal. The first one, this is the input sinusoidal waveform. So the VPP, the peak to peak is 20 volt, the amplitude is 10 volt. So 10 volt sine wave, 10 volt sinusoidal signal, the input signal. And then the output signal, so what is the output signal? So it's very simple, right? It's just a level shift. It's just a 0.7, so base input and emitter output. So just 0.7 level shift. So it is still the sinusoidal wave. But the average is different. So if you look carefully, there's still a difference between these two. So what's the difference? The DC level of the input signal is 0, right? But the DC level of the output signal is what? Is negative 0.7 volt. Negative. I want you to pause. Maybe you should pause. And then you see the minor difference between the output and the input. And then let's move on to what about the collector current? Remember this? The collector current of Q1. The collector current of the Q1 seems when you have the sine wave, the sinusoidal signal, then it's still a sinusoidal signal. And then what's the DC level of the collector current of the IC1? So why is the 10 milliamp? Why the quiescent DC current? Quiescent DC level of the IC1 is 10 milliamp. So why is this? So I want you to pause for 5 minutes and think about this. So the question is, why the quiescent collector current, the DC level of the collector current waveform is 10 milliamp. Let's pause for 5 minutes. So I'm back. Let me explain this. I said the VO is the VPP is the VP is the amplitude, the amplitude of the signal, the VP sine omega t. And then the load current is divided by RL, right? Still a sine wave. And look at the green note. So the bias current IQ plus the purple one, the purple current, equals the red current on the top. And then to answer the DC level, the average value of an AC signal of a collector current, so you need the time average. You need the time average collector current. So the DC level means the time average collector current. So use the average calculation, so 1 over T, and the integration for a period 0 to T. And you plug in the collector current, the constant plus the purple one, and you do the integration over a period. So the answer, because the sinusoidal signal, the time average of the sine of the second term is 0. Right? So you get the IQ. So we need this for the upcoming lecture. Okay? So here's the takeaway, the first one. The learning objective of this lecture is I use the tool, the simulation, to help you become more confident about knowing this Class A upstage. So you get a deeper understanding about the Class A upstage. Number one, remember the definition of Class A. The definition of Class A, conduction angle 360 degrees. And I used the metaphor. I said, in our life, you have the mountain, you have the valley, but it's still alive. Never give up, right? Conduction angle 360 degrees. So now you see this. So it's the fully on. Okay? So the definition of class A, the first takeaway. I make the connection. I use the simulation, make the connection of the real case and our definition of class A. So just takeaway number 2. So I use two examples to illustrate the difference between these two scenarios. The first one, I use the 1 kilo ohm and 2 kilo ohm, two different load resistance, to exemplify these two different scenarios, to explain the negative in these two, to explain the negative saturation voltage in these two different scenarios. Number 3, time average collector current. The time average collector current is the same as the bias current of the current mirror. The time average of the emitter follower current is the same as the bias current. So 3 takeaways. I hope you get the deeper understanding about the Class A upstage through this lecture. Thanks for watching.